All right. So, welcome back, geometers. I don't normally include the bell ringer in these, but we have so many people out that we might as well. The question today is, if this is an alien footprint, and the big toe is on the inside, right? Okay, here's an alien's footprint, and he's going to walk a straight path, or they are going to walk a straight path. If I want to generate this image, I assume that the next one's probably somewhere in here. Now, I want you to tell me what I've done wrong with this. Yeah, your toes aren't the same on both feet, and thank goodness, because it helps you balance. The pictures aren't going to be great. We're just going to assume they're the same. Does your next one wind up about here? Okay, and I'll even draw it a little bit better because I can do better than that. Where's the next step after this? And before we even do that, how did you get here? Because I heard Elijah saying something that I liked, but I saw a lot of people saying it. How did you get from here to here? Okay, so what about with geometric stuff? We reflected. So if I reflect, and I'm just going to do it with my left hand, I'm here. And then I do what? I translate. Now, notice the direction that I translated is exactly the same as the direction that my line happens to go. And we'll summarize that. Okay, if I want the next step, what do I do? So reflect and translate. And reflect and translate. And all of a sudden, we don't have to store every possible footprint image. We can say, oh, if the person's walking however fast, you're going to generate footprints by reflecting over the line and then translating it. And then you're just going to repeat that. If the person were to speed up, would their footprints change? How? Yeah, if my next footprint is here, hypothetically, what has this character done? So maybe, like, I don't know how fast they're going. Do we agree they've gone faster? Because if I'm walking slow, my footsteps are really close together. Maybe they're slowly, I don't know why they would do that, but they could be doing that, right? This doesn't tell me anything. Okay, the important part of this, 2, we see a real world connection, and I'm like not even pulling your legs at all. If that saying is weird, that's messing with you, right? This is how your computers think about these things. We don't want to have to store all the pictures. We just want to be able to generate them easily and quickly using a simple rule. And you guys have picked out quite a bit of that rule. So back to our notes, we will reference this over and over if you don't mind. All right, today's lesson is super quick. And realistically, the bell ringer has pretty much covered all of it. Man, I hope I can see a footprint when I leave this room. So definitely not. I'm not. But here we go. Let's knock this out because I'd like to give you guys time for homework. So here we go. In 3.4, our focus is going to be on how do we actually go about, or how could one classify rigid motions. And there's a couple things, we get a couple theorems today that are pretty cool. That one of them to me seems obvious when we think about it. The next one, less obvious, but we're going to see that we've actually been doing it. Yes, sir. Tuesday we took the quiz. Is that true? Yeah. Yesterday. I will check. There should be a video. I'll find it. If it didn't save. We might have had a really short one and then work through the homework. Oh yeah, work through the homework assignment and make a note card. Yep. Cool. All right. So we're classifying rigid motions. Now, if I put 2 rigid motions together, there's a word that we use to represent that. Like on this one, I reflected over the line, and then I translated, and then I reflected and I translated, right? When we put 2 together, what's it called? Starts with a C. It's a composition. So, nice job checking your notes there. Check it out. In classifying rigid motions, we are going to be looking at how do we classify specifically when composing, and I'm going to use the fancier word, isometries. But remember, isometry is just a fancy word, or isometries is just a plural for rigid motion. It is a single word, doesn't save a ton of letters, but it sounds way fancier. Isometry, rigid motion. Cool. So as we're looking at these, right off the bat, we get a theorem immediately. And your book, while the book will prove stuff using paragraph proof or flowchart proof, what do we always use? 2 column, and we have not done a lot of proof this chapter. I've gotten a lot of emails whining about that, so don't worry, we'll get more proofs. Okay, No, not really. But I appreciate that you believed it. Cool. So, theorem 3.3. And that felt kind of rude. I do feel like my voice is sincere even when I'm trying to mess with you, which is intentional. Anyway, 3.3. If two or more rigid motions, or isometries if you'd rather, two or more rigid motions. What are the possibilities for rigid motions for us? Love it. Rotation, reflection, translation. If two or more rigid motions are composed, which we've seen that, but we'll look at it again, then, and I'm going to pause right here, and you guys are going to help me reach this conclusion. And I'm going to do it on video, I suppose. Yep, I'll do it. You know what? Pause. We're going to use GeoGebra. Then the overall change, or the overall transform, if you would rather. If I didn't change shape or size, I'd use what word to indicate that? These are motions that are what? Rigid. Was the overall transformation here rigid? Boom. I don't change size or shape if I compose a bunch of rigid transformations. I can reflect, rotate, do whatever, as long as I'm not doing that dilation, which is one that we haven't talked about yet. I don't change the size or shape, just the location and orientation. Okay, this one. Do you guys agree that feels obvious? If I don't change the shape or size at any point, then the shape and size shouldn't change. Okay, like that one seems silly to be called a theorem. Immediately, we are going to transition into what we saw in the bell ringer today. Now, this is a unique section because there's only one topic. It's just composing these things. Okay, within these compositions, the one that we did for the bell ringer today is a special one, and it gets used all over the place. What are the two rigid motions that we composed to make those footprints? We reflected and translated. Now, because they are so common in computer science and geometry, it gets its own name. When we take those, and we'll define this here in a second, we have what is known as a glide, is how I refer to it, but the proper name is a glide reflection. I will simply say glide because it's understood within this context that we're going to do exactly what this says. Okay, now, to define a glide, I'm going to try to do it really mathy. I'm going to write just the mathy stuff, and then we'll talk to make sure if we need the wordy stuff, we will. But here we go. For our picture, if I have to close the blinds, I will. As long, it'll keep snowing, I promise. And I know that you're excited about it. We'll talk here in a minute. Okay. I didn't hear what you said. I just said okay. I don't know why I did that. Check it out. If we're gliding, here we go. This is what I want to put for the definition. I have T, X, Y, whatever that means, circle thing in the middle here, and then an R, L of this triangle A, B, C. Okay, I have written on the board in the pure notation that we use and our book uses, two transformations that have happened. And this is a glide. This right here, right now, is a glide. And I think it's about what we did here. We're going to have to say one more little particular piece to this. What is this saying I'm doing? I'm reflecting over which line? L. This thing says I'm doing what? A translate, and along the vector, which is this, XY, right? Okay, so a glide is just a composition of a translation and a reflection. Where, we need one more little part. Where, or such that, if you'd rather, whichever one makes more sense to you, the vector xy, whatever this is, it's a line segment, so it's just an arrow that points in a direction. Whatever this is, it better be parallel to the line that we reflected over. Now, what I mean by that, and it's really easy to demonstrate, but if you're watching the video, you won't be able to see it. If I were to want to model my footprints, and it's not perfect because a human gait doesn't work really truly straight, but the footprints that we did on the board is close to reality. If I went over this, I don't think anybody, when you did this one on the board, I don't believe, I didn't look super closely, anybody's next footprint out here instead? And that one doesn't even look that off, I don't think. It's a little further away, but maybe that's just a mistake, right? If I went again and I'm up here now, is it obvious that it's off? Okay, what's this person doing? Maybe, but they're doing it like in an obnoxious way, right? Like they're going and they take their first step, that's all fine and dandy, and then they go, like, who walks like that? You can only take like 4 steps, right? We can't do it. When you guys did this without me having to say it, when you translated, I think that the natural choice was for you guys to pick a translation vector that is exactly parallel, because that's a natural thing to do. Now, real human beings, their feet are a little bit like this, not a ton, but you really do see this, so there's a little bit more going on. However, we need to, and we all naturally try to use this. Okay, the bell ringer today was a glide reflection. That's what it was. Now, when you guys explained it, and I just don't remember, did we reflect first or translate first? I think we reflected in here. Does it matter? If I had translated first and then reflected over, would it wind up in the same spot? Yeah, the order here is irrelevant as long as you get both of them. Okay, is this enough of a definition? A reflection and a cross line L and a translation along a vector where the vector and the line are parallel. Cool. All right, so right off the bat, we jump in to our second theorem of this section. So it's still in the same within glides or beneath glides, and we just call this theorem 3.4. And here we go. All rigid or all compositions, here we go, all compositions of rigid transforms, which we've seen several of them already. But remind me just one more time, what are the 3 rigid transforms that we have? So if you give me any of those and compose any number of them, we get a composition of rigid transforms. Now it turns out that no matter what it is, doesn't matter how many there are and which order they're composed in, all compositions of rigid transforms can be represented, I'm going to say drawn or found with a single rotation, reflection, or translation. Now, this one is not quite as obvious, but we'll see that we get another extra little piece here in just a moment where it will become. What we are saying with this is it doesn't matter how many little pieces I do, all compositions, and I'm going to go back over here, and I'm going to hide a couple of these just so we only look at the beginning and the end. And let's see here. I'll take this one and this one, and I'm going to hide those somehow. There it is. Okay, we'll hide you and you. Do it now. Won't do it. It wants me to pick the points. There we go. Okay, I don't know if this is really going to work or if it's worth the time, but I would like to hide those. Hide them. Get out of here. Okay, I can't hide them. Can we pretend this one and this one's not here? Okay. If I wanted to get from here, here, the original, to here, do you guys see a single thing that could make that happen? It looks about like a rotation, and I don't know the exact piece, but I know that if I take this, and I'm just going to place a point arbitrarily in here, and we can see we'll probably get close just by guessing. If I put 1 point, that's the same distance from B double prime right here, or B and B double prime. It's probably about right here, I think. Close. Do you guys agree with that? Now, this isn't going to be perfect, but I do just want to show. I did a lot of stuff to get over to this triangle that we had, and now it's hidden for some reason. There it is. I did a lot of stuff to get over to this triangle, right? We reflected, we rotated, we translated. Tons of stuff. If I put one more point roughly here, and then I select this guy and I rotate it about that point, help me pick an angle here. We're going to rotate about a point. We're going to rotate this about this point. How many degrees do you think I need to rotate to get to here? It's probably around 180. It's not going to be perfect. A little bit further than that. Could we eventually land on it, you think? Now, we might have to move the point around, and I wish that I had this prepared. It's way off on that one. That was a bad guess, just for the record. That was my bad guess, not yours. With this, I should have had one prepared to show it, but we can certainly get there. Now, what's nice about this is, first and foremost, just to clear things up, what's a theorem? Ooh, it's proven true. How long has it been true? Forever. How long will it be true? Forever. And it's always my thought when I think of that definition, better than diamonds, right? Diamonds aren't really forever, but theorems are. Okay, I don't think we've seen this word yet, but we're going to sneak it in. If we have a theorem, which we do, right here, and it's true, it's been proven true, we're not going to prove it, but it's true. Is it possible that there's a special circumstance that results from this statement that we could write as another theorem? And in fact, we're going to do that. I'll just say it is possible that this leads directly to a more specific case. In that situation, these are referred to a little extension of a theorem. This is known as a corollary. Okay, a corollary, and I'll spell that and I'll write it bigger so you guys can all see it. C-O-R-O-L-L-A-R-Y. A corollary to a theorem. Depending on where in the world you are and who's writing the text, this could be its own theorem. But all a corollary really means is, hey, here's this, and here's an extension of that idea in a particular case. And I think we've actually seen this corollary before. Instead of a translation, can I make a translation with reflections? How? How can I make a translation with reflections? If we have a theorem from a few days ago that if I reflect over two parallel lines, and I can draw the picture here, you don't need to draw it again, but if I take this and these lines are parallel, if I reflect this triangle, it's really easy to do. All I have to do is translate it. How much is the distance? Twice the distance between them. I can make a translation with two reflections, right? Can I make a rotation with reflections? How? If I reflect over lines that aren't parallel, it winds up looking like a rotation in the end, which, check this out. We just decided that we could make a translation using reflections or compositions of them, but I could also make a rotation with composing reflections. Can I make a reflection with a reflection? That's a silly question. It sounds odd. Yes is the obvious answer, right? It's just a weird question. Can I make every single one of these then with just reflections? Whether it's a rotation or a translation or a reflection, I could do it with just reflections, which that's what this theorem is saying. They didn't specify, but here's the corollary, the extension of this that could be its own theorem, but maybe it's not worth it. Everything, all transforms or rigid transforms, all rigid transforms can be written by composing reflections. So the original theorem said that we can just do it with another rigid motion. Turns out we can even do better than that. We can do it just with reflections, which means that now if I have a computer program that I want to be able to rotate stuff and translate stuff and reflect stuff, well, maybe I only need to really teach the computer how to reflect and just tell it to do it a bunch of times. That is way less labor intensive than saying, here's a rule for this situation versus this versus this. It could all just be reflection, and we can save a ton of our processing power. Okay, we have one example, and then it's homework time. For this, I'm going to give you guys a couple minutes for the following problem, because I want to see what you come up with first. It is nothing new, I assure you. Everything that we've seen shows up here. Before we do this, to save time here, I'm going to do a little bit of editing magic, just for the people watching the video to shorten it up. If you're watching the video, I want you to draw and try this problem. I'll resume it so you can take a peek, and then I want you to try it. Excuse me. We have the mapping up here on the board. Your job right now is to find the glide that moves us from here to here. What do you think might make this so much easier? A graph. Does it have to be perfect? No. If you can sketch a rough graph on your page, I'm cool with it. But because I'm nice, I'm going to come around with some graph paper if you'd like it. Cool. It's not the sticky notes. So I'm trying to find a single glide to go from green to red. And everybody did a pretty good thing first. You reflected over the axis, and I'll trace this first, I suppose. I like this idea, and it's a good idea if we're just looking for any composition. That's all fine and dandy. I think that reflecting it first is a natural choice, so we could just reflect it, and then we just move it left and down. There's an issue, though, because the reflection, if we did that reflection, what do we reflect over? the y-axis, which means I now need to have a translation parallel to that, which means I can only either go down or up, but I'm never going to wind up on that figure. So the idea is good, and you're not wrong. It's just not a glide. So we need to change something about this. Now, there's no right or wrong way to start this, as long as it's one of the following two. What does a glide consist of? Okay, what do you want to try to knock out first? So translation. Okay, I don't care which point we look at, but I think I can see it. I can only, I'm going to try to only move up and down if possible, or left and right if possible. If I wanted to get from C to C prime, how far down do I have to go? 3. Now, it happens to be straight down, which is pretty convenient, but I just want to check. To get from this B value at 2 down to this B value at -1, would going down 3 still work? Okay, and we'll just check. If I go down 3, 1, 2, 3, which is totally arbitrary to pick that first. It could have been the reflection first. This is where I would wind up. Okay, if we translated straight down, which is what we just did, is there now a single reflection that would take me to land on this? Okay, what would you have me reflect over? So if I do the y-axis, here it is. And they're not quite the same. And you did, I agree with you. So that one didn't quite work. But what else could I reflect at? Like, notice C and C prime are the same point, right? If I reflect over this, and I'll actually reflect it, so I just had to make sure that C prime is still there. If I reflect over that and put C prime back in the same spot, did it? Hey, that's pretty handy. Now, any of you guys ever feel like you get goofed up on keeping straight what x equals a number and y equals a number looks like on the graph? I don't believe you guys, or people are thinking and they're not answering, which is fine with me. Is x equals a vertical line or a horizontal line? How do you remember that? Okay, the x is always the same. It's what is x always equal to? So it turns out as long as we realize that it's a reflection and a translation, it doesn't really matter which one we do first. If we translate first, how far down did we have to move it? And how far in the x direction? None. Okay, so there it is. This is straight up and down, right? And then if I want it to be a true glide, I need to reflect over another straight up and down line. What was the x coordinate that we wanted to reflect over on ours? -1. Now, does it matter if I translate first or if I reflect first? Like, here's my reflection first. Could I now just move it downward? Hey, it works either way. It doesn't matter the order they show up in. Based on what I've written down, which one happened first? The translation or the reflection? It's the reflection, because whatever's closer, right? So what line did we reflect over? What was x always on that line? And we reflected triangle ABC. Here is our singular glide that takes us there. It's a reflection and a translation. The order of them does not matter. Okay, this problem is the least mathy feeling problem that I can recall from like all of geometry, because it doesn't feel like we're doing any math. We're certainly doing logic stuff and we have to reason it out, but there's not a set, just standard, always follow this procedure. After we've looked at it, does it feel at least approachable if you had to do one on your own? Okay, so with that said, I want us to get an assignment. And here we go. Hey, that was third hour. That's really convenient that I still have it because it's the exact same lesson. Cool. All right, fifth hour, here we are. We're going to add this to the assignment list. So we took the quiz yesterday. I'll have it graded for you guys tomorrow. If it didn't go well, I would already start thinking about what you're going to say when you come and ask for a way to fix it. Like, I have no idea how you guys did. I haven't looked at them at all, just for the record. Okay. We're going to get it here. For the homework tonight, you get homework 3.4. And we're going to look at number 11 together, just really quick. I'll even look at it in my book. I'm fine with that. Cool. We get homework 3.4, page 136. You get problems 11, 13, 17, 18, 21, and 25. If you would like to take tracing paper home tonight, do it. Like, I have a bunch of it. Feel free to take a couple sheets. Don't take like 500 sheets. But I want to look really quickly at number 11. Okay. I'll put that back up on the screen here in a moment. On number 11, here it is. They are asking me to find the vertices of a new triangle after I reflect across this line and then translate it a certain amount. Now, as we're looking at this, they give you a graph. Do you think they do that just for fun? No, they give you a graph because what's going to make this problem easier? A graph, being able to envision it. Now, this problem feels like a little bit of algebra, and I'm just going to reread. It's a line that crosses through P and which other point? Y at -2, which is all the way down here. If you elect to draw in your textbook, so long as you do it in a light enough way that you can erase it, I'll never know. Okay, if you would, rather just have it in your notes, I'm fine with it. This is my book. Nobody else is ever going to get it, so I'm just going to draw this line. If I physically draw this line, does it make it easier for me to see the reflection? So you might say no, and that's okay, but check it out. If I look at this point C, if I go diagonally, here and here, do you agree I went 1.5 diagonals? From C to this line, I went 1.5, which means if I reflect it, it's 1.5 away over here. Here is C prime, and I can see these things happening. If you draw in the book, erase it after the fact. If you'd rather just sketch it roughly or take a piece of graph paper, I'm cool with that, and you can do it all the same. Sweet. Don't destroy my books, but loose drawings that you erase, I'm cool with, or light drawings. Sweet. All right. Yep. It's also up on the board on third hour, but I'll write it up for us too. Those of you that are traveling for stuff, please remember to send me a picture or bring back your completed notes and the assignment.